Alright, welcome back to another analysis video on experiment 2, accelerating down a ramp. Now this is going to cover the dot point of module 1 inquiry question 1, dot point number 4. So it says conduct a practical investigation selecting a range of technologies to record and analyze the motion of objects in a variety of situations in one dimension. Okay, so last time when we did this, we looked at using dynamics trolleys and tick timers. Today we're going to use this little apparatus here, so I'll go into a bit more detail with that shortly. Okay, make sure obviously to go through your little risk assessment. What are the potential risks? If you're using a ruler, please don't whack each other. If you have plasticine, please don't eat it. If you have a ball bearing, please, if you see it on the ground, don't put your foot on it and slip over. That's the idea. Okay, so that's the dot point we're covering here, as you can see. Just to go through why we're doing this particular experiment, it actually is quite similar to something that Galileo Galilei did. But Galileo Galilei was the guy who determined that objects fall or accelerate at the same speed. Now, the idea, this picture you have here, the old idea, so to speak, is what we call Aristotelian physics. So Aristotle came up with the idea that heavier objects would drop faster than smaller or lighter objects. Galileo changed that perspective by finding that it doesn't really matter how heavy they are, so long as when you drop them, it is in a vacuum of space. So a vacuum of space means a place where there's no wind. If there is wind, then the heavier object can go straight further than or faster than a smaller object. Now, there was the famous experiment of Pisa, so as you can see there, it didn't quite work out for Galileo because there's too much air resistance, so he used this little apparatus here instead. So he had a ramp, and he rolled the ball down. Now, it doesn't quite give you the exact, it doesn't accelerate as fast, but because it doesn't accelerate as fast, you can observe the motion a lot closer. And what you'll find in your experiment, if you do have an additional marble ball to work with that's slightly bigger, you can roll it down at the same height as a small marble ball, and you'll find that they pretty much end or reach the bottom at about the same time. So the formula we're dealing with here is the final velocity will be the square root of 10 times little g, which is the acceleration due to gravity. Might just write that down, just in case people get confused. So little g here is acceleration due to gravity. H here is the height. Okay, and we have a value of 7. Now you don't need to know how we got this form. This isn't actually part of the syllabus, but it will be important in our analysis, because what we're going to do is we're going to accelerate this object, this marble ball, from this point here all the way down there. Okay, and we'll find its final velocity, because we will also be able to calculate its displacement and time it takes. From there, because we also know the height at which we release it, if we rearrange our equation, we should be able to work out what is the acceleration due to gravity. So that's the point of this experiment, using this apparatus to find out what the acceleration due to gravity on Earth would be. So I'll just come back to this diagram here to kind of do some labels and to explain how everything is supposed to come together. So the height that you measure, so there are a couple of things you need to measure. One is the displacement. Well, that's not a very good color. So we need to measure out the displacement, so from this point here all the way to this point here. Now this displacement is to be kept constant. Okay? We are not changing the displacement that the ball travels throughout the experiment. We're going to do about 5 different heights, but displacement will stay the same. The thing that we will change is the height of the ramp. Okay, so we're going to release the ball here, and then say after 3 repetitions, I lower the ramp. Okay, so it comes kind of like down here, lower angle, but still same displacement, and then I release it again, like that. Okay, so I'm going to change the height, but where I release it, the marble ball should still travel the same displacement, and that's key. Once you've found that, obviously start timing here. So your start time is here, 0, and then your end time is when it passes the ramp. Okay, so there you go. You have where to calculate the height, you have where to calculate displacement, and you know the timing there. Which means by the end of it, you should be able to work out the velocity of this object. Now, this equation seems a bit different from what we've done, but it's actually something derived from something that we already know. So to just show you, if an object is accelerating, okay, so it has an initial velocity, and then it accelerates, this is the formula we demonstrate by to show how far it's moved, right? If something is falling, so you just release it, there is no initial velocity. So if I'm just releasing the ball here, and it goes down here, there is no initial velocity. So I'm left with 2a t squared s, okay? But, you know, I don't want to just find acceleration here. I want to find the final velocity component. Because this acceleration that I have here is just going to tell me how fast it's accelerating along there, but not what gravity is doing to it. And I don't actually know what the final velocity is either at this point. So I need to find the final velocity. So if I just rearrange my equation, so half times it over, so it's 2s, okay, and then I'm going to leave the t squared over here just for now. You'll see why in a second. We know that velocity is equal to, or acceleration, sorry. Acceleration is equal to final velocity minus initial over time. If I substitute that into my equation, this is what I get here. Okay? For those of you who are quite mathy, you would know that 1 over t times t squared, they will cancel each other out. Well, not quite cancel, but you'll still be left with a t. And we also know that u is still 0. Okay, so I'll just give myself a bit more space here. The new equation will look something like this. And then if I just rearrange it, so 2s over t equals to v, that's exactly what we get there. So that's how we got that equation. Okay, so part of your quest in this investigation is obviously to collect some data. Now, the important point is if you want to graph something, graph a trend, you need at least 5 different data points. That's just to give yourself enough trials to have a reliable trend. Okay, so we're going to look at 5 different heights. I gave you a starting height of 0.05. What you should aim to do is to spread it evenly out. So that's what I did there. If you go at a height bigger than 0.3, so like 30 centimeters, it does get a little bit hard to record because the ball, the effect of gravity will be stronger just because of the angle you put onto it. Give yourself a nice little time or distance for you to work with so that you can actually measure the time. Give yourself a bit more time to react, I guess, would be the saying. Find the time. Initial velocity will definitely be 0 unless you actually put some kind of force when rolling on it. Final velocity, calculate it using the formula we talked about just then. And then we're going to do final velocity squared. And then we're going to find the average of the velocity squared. Okay? I'll explain why we do velocity squared in a second. But at the end, you're going to be graphing velocity squared against the height. Okay, so let's look at the line of best fit. When doing a line of best fit, or actually when plotting a graph, always have a title, so a descriptive title that says what you're going to do. You are then going to put the name of the independent variable. So the dependent variable, and I'll write this down in case someone wants to copy. The independent variable is basically what you measured. So what did you measure in the experiment? What was the thing that you were trying to measure? Well, I was actually trying to measure the velocity, and I'm graphing velocity squared, so that was the thing I was measuring. What was the independent variable? So what was the thing that was being changed? Well, that's quite easy because we already talked about trying to change the height of the ramp. So the height of the ramp in which we release the ball, that's going to be our independent variable there. Okay, so you'll have to graph this out manually. I did this digitally, so that's how it looks here. Okay, so that's what we have. Now I have this as v squared and then height there. Now there is a reason why it is v squared. It actually has to do with the formula we are looking at. Okay, and we'll talk about that in the next slide. If you have a look here, okay, this is the line of best fit. You can see that the dots aren't being connected to the line. The line of best fit just kind of goes in between the middle point of all that. Now, a good line of best fit should be able to go through the average middle point separation of each of the dots you use for your experiment. So that's how you use a line of best fit. Okay? So what does that actually tell us? Well, let's just write it out first. The gradient is equal to our rise over run, which is, the rise is v squared and the run is h. Okay? Now the formula that we looked at earlier, velocity, final velocity equals to 10 gh over 7. Yep, 7. Okay. So let's try and rearrange our equation to make v squared over h the subject of the equation. So let's rearrange that. V squared equals to 10 gh over 7. Okay. Then I'm going to divide both sides by h. So v squared over h equals to 10 7 g. Well, have a look at that. What we actually have here right now is this is our gradient value. And this is obviously little g, which is acceleration due to gravity, and then 10 over 7, which is a constant. That will help you find the the gradient essentially is a constant that will help you find g. That's what we found. That's why we graphed it as v squared over h. If we graphed it as v over h, it wouldn't work because that's not the formula that we can apply to in here. So it's not quite applicable. Okay? So that's what we're dealing with here. Okay? So I might just quickly show you how to do the end part, and then I'll show you what my value for g is. So we found a gradient. this one here. So it is 13.12 equals to 10 over 7g. So 13.12 times 7 over 10 will equal to my acceleration due to gravity. So let's have a look what we have. So exact same thing as I talked about here, rearranging everything. You can do your substitution first, there's no right or wrong to that. And I find that my acceleration due to gravity is 9.18 meters per second squared. Okay, so it looks pretty close to 9.8. There's another little test we can do to see how accurate we are though, and that's called the error percentage. The error percentage is just designed to have a look at how close I am to the actual answer. So when we talk about accuracy, how accurate something is, we're talking about exactness. How exact is the experimental value to the theoretical value? Okay, so that's what we're going to do. This is the formula to use. When we say accepted, we can also say it's the theory value or the theoretical value. Experimental value is what we found. So it's the absolute values of the accepted minus the experimental divided by the accepted value, oh, there shouldn't be an E here, times 100. That will give us the percentage. Okay? So the accepted value of acceleration due to gravity is 9.8. Subtract that by experimental value, 9.18. Absolutes divided by 9.8 times 100, and I get about 6% in error. Now, this does vary between the type of experiments you do, but generally we say if the error percentage is smaller than 5%, we have a pretty accurate experiment. Okay? If it's above that, then it would be, so in this case, we would probably say it was inaccurate. Okay, and this is one of the key things in experiments where they ask you in physics, is this an accurate, reliable, valid experiment? You can't be hesitant. You can't just say, I know this number here, 6%. It's a very small number, but it's still small, but it's still bigger than 5. So it's an inaccurate experiment with areas you can improve on. And then you can elaborate, the percentage wasn't very big, some minor things you can do. If you were to say it was kinda inaccurate, you know, or maybe perhaps you say somewhat, those aren't really decisions. Those aren't really decisive decisions, and you wouldn't be paid marks of that if you were assessing how reliable or how accurate something was. So please make sure, be very confident in writing out if it was reliable, valid, or accurate. Okay, just the last bit I want to emphasize on, because you will have to do a little response writing for this. Reliability means dependability. Okay, the best way to get reliability is repeating your experiment, but the only way you really know if your experiment is reliable is for the same trials. So for the same trials, you have consistent data. Okay, let's go back to the table and I'll show you what that means. Okay, if you have a look here, let's use the 0.05 height. If you look at the time we get, okay, we'll have a look at this time here, 0.87, 3.87, 3.93, 3.88. Those numbers are very similar to each other, so they're quite consistent. So for that particular trial, it was reliable. Okay, so that's kind of how you can see reliability there. The next one we have is validity. Does the method measure the variable you're testing? So have you made everything controlled and only have one independent variable? That's quite important. So if it's a valid experiment, you can only have one independent variable. Everything else needs to be controlled. Did you do that? The last one is accuracy. How close were you to the exact answer? To improve accuracy, use more exact measurements. So perhaps if you use like a meter ruler, perhaps in that meter ruler you would want something that goes into millimeters, or measuring in millimeters, or maybe even micrometers. So that's how you would improve accuracy on that scenario. Do you have any other questions? Please let me know. And there are some other links to other experiments in here as well.